Now I think we understand the underlying physics of inductors well enough to try now an example. So this is our second example of the circuit consequences of Faraday's law. So here's the circuit that I want us to consider. What we're going to have here is some battery with some EMF, I'll call it curly E, and then it's going to be wired in a circuit, and that circuit is going to have a switch S that we can have either opened or closed, and then after that switch we're going to go into an inductor, and the standard circuit symbol for inductor is in fact a little curly Q like this. It looks a lot like a solenoid in the sketch. That's the standard symbol. And then after the current goes through that device, there will be a resistance R, and then I will close up the circuit like so. So this is a standard what is known as an LR circuit because it has an inductor and a resistor in it. Now, what else we are told about this system is that for times less than 0, so for t less than 0, the switch is open, as I've shown to you here, right? So for times less than 0, the current flowing through this circuit, I of t, is going to be equal to 0. Then what's going to happen is that at time t equals 0, the switch S closes. So we're going to, close the switch and thereby make a connection, electrical connection. And the question is, what then is the current going to be I for times t then after 0? How will this thing behave? Now, in terms of analyzing a circuit, as we've been taught, the F equals ma of circuit analysis always are Kirchhoff's laws. Now, the first Kirchhoff law, as we know, is the current law. And in this case, because I have everything really wired here in series, we know that whatever current that flows out of this battery, which we're going to call I of t, that's really what we meant by the current flowing through the circuit. That's the same current then that's going to go through the switch. That same current that's flowing into this corner will come down, so that will be the same current flowing through the inductor, and also then through the resistor, and back in then through the battery. So that's pretty straightforward. But now that we know that the current, our presumed direction of current flow is in this direction for each of the circuit elements, we know then we're presuming the current I flows down like this, which makes the sign convention that the top side, or the mnemonic for remembering signs, is that the upstream side of the inductor is regarded as plus in our equations, the downstream side is minus, and similarly, because we have the same current flowing around the circuit in this direction, we similarly have the upstream and downstream sides of our resistor. Next, we apply the effective second Kirchhoff's law, K2. And to do that, of course, what I want to do is set 0 equal to the sum of these effective voltages as I go around my circuit. I'm going to choose, what we usually end up doing. This will be my starting and ending point, and I'm going to perform my Kirchhoff loop by going this way here around my circuit, standard kind of direction. So let's see what happens when I begin to do that. When I do that, the first thing I come across from this X is my battery going from minus to plus. So that's plus or minus the EMF. But we've gone from the minus to the plus side, so that comes in with a positive sign. The switch and all the wires are regarded as ideal. I have my inductor next. And when we go across an inductor, as we've just said, that's always plus or minus times the inductance times di dt. And in this case, we happen to be going from the conventional plus to the minus side of that inductor going downstream. So that always counts as a minus when we do things like that. And then finally, as I come across my resistance, I'm going from the presumed plus to the presumed minus side. So then, once again, that would be plus or minus IR, but in our case, it actually ends up becoming minus. Very good. So now we have our basic key equation. We can rewrite this, tidy up the equation here a little bit for ourselves. One thing that might be nice to do would be actually to, let's see here, I'm going to move my inductance, I guess, to the other side of the equation to get a nice differential equation. So that would put L times di dt on the left-hand side of my equation by moving this term to the other side. And what's left then is E with a plus. That's the battery EMF, and then minus I times R. So that will become then the governing equation for this particular inductor. Next, we're going to want to solve this equation. But before we try to solve an equation like this, it's always good to try to make a guess at what the various behaviors are going to be. So here's our guess for the solution. It's always good when you're trying to guess what the general behavior of something is going to be to try to make some kind of a sketch of it. So let's put down some axes here, right? So I'm going to be plotting on this axis the current I as a function then of time t, like so. And now we have various limiting cases to consider. The first thing we know, of course, is that before the switch closes, which happens at time t equals 0, before then, of course, we know the current is going to be 0. And now we should ask, well, what happens right at the instant when I flip that switch? What is going to happen to that current? And the answer to that, right here, this is when we flip the switch. When we close the switch. Now, when we close that switch, we have to remember we are obeying this equation. And one of the interesting things there you'll notice is that when I close this switch, if I look at the right-hand side of my equation, I've got some value for E, some value for the strength of the battery, right? And the current actually, right at the moment when I flip the switch, happens to be 0. So what I find is then this combination of things, the derivative of I, in fact, is not, the derivative of I is some finite number, right? It can't be infinite. And that tells me something very important, because if you were to guess that the moment we flip the switch that the current maybe takes some kind of big jump, like it would jump up something like so, and that there were a discontinuity here, if there were a discontinuity, right, the slope at that point would be infinite. That would mean this side of my equation would be infinite, but the right-hand side of my equation is just the voltage on the battery, maybe minus some value for I times R, but it's finite. So I can't have any discontinuity like that. It actually has to be a continuous function. So let me erase that, right? So there's not going to be any discontinuity. We'll just have a normal thickness here for our axis. And the current is going to have to, sure, the current is going to want to start to flow, right, when I close the switch. And the current is going to want to eventually flow in this direction. So the current will increase, but there can't be any discontinuity. So we close the switch, there has to be no discontinuity. Because di dt is finite. So that means then the current has to do something like this. It has to come in and hit that value 0 nice and continuously at time t equals 0. Now, so that's kind of the first real lesson that we've learned here. So there's some general lessons for inductors. And we had similar lessons, by the way, for the case of capacitors. But the lessons that we learned here are, first, that whenever you flip a switch, whenever there's some switch that flips, the current has to be continuous. I through L is continuous. What that means is that the effective voltage, this L di dt term, is going to assume whatever value, right, is necessary in order to keep that constant, right? That's what an inductor does. It tries to resist any change in current, because that's how you resist any change in flux. Now, let's see what happens when we go to long times. Well, when we go to very long times, right, eventually, of course, we're going to get some flow of current, and eventually we should settle down to some kind of a steady state where things stop changing. Now, when things stop changing, what we know then is that this derivative, di dt, will have to vanish if I isn't changing anymore. And if that vanishes, that means this side of the equation is 0, and then we can solve for the current very easily. We just have 0 equals E minus IR, or if you think about it, that just means E equals IR, where I, the current, is the EMF E divided by the resistance R. So there's a certain value up here, which is the battery EMF divided by, or battery voltage, divided by the resistance R, and that's what things are going to settle down to. So the behavior of the curve that we are guessing at, that we expect, should somehow at long times approach this constant value, and at short times it has to come into 0. So we expect then it's probably going to have some kind of a general behavior like that. Now, here's kind of the really neat thing. Once we get to infinity, right, so as we approach the steady state, look what's happened to the effective voltage across my inductor. di dt vanished, so L di dt is going to be 0. So at long times, when we reach steady state, the voltage across an inductor just becomes 0. And that's kind of nice in terms of what the diagram looks like, because in the diagram, the inductor actually just looks like a wiggly wire. And since it looks like a wire, and we know that a wire, an ideal wire at least, with no resistance, always has 0 voltage across it, what we can say is that at long times, when we reach steady state, we can treat an inductor just what it looks like, which is a simple ideal wire. So as we approach steady state, the inductors just act like wires. So those then are the behaviors that we would guess at if we were to solve this particular differential equation.